Hi, my name is Monserrat Jimenez, and this is my argumentative exam. For the first problem, we have this circuit, which is the one that we will carry out the complete nodal analysis. Well, first of all, we have our target variables, which are voltage 2, 3, 4, 5, 6, and 6, 7, and 8. We have here our nodal equations, then we rearrange them to finally write them in matrix notation, where this is G, which is the conductance matrix, this is V, which is the voltage vector, and this is K, the source vector. Then we have our MATLAB code, which shows us the voltages, which are these ones. And then we have here the circuit lab circuit, and these are the voltages that are shown in the circuit. There are little discrepancies, but they are pretty similar, and they are because of the roundings of each subword. And well, this is the voltage drop with its respective electric current, which is the same as, well, the given in MATLAB circuit, but with the small discrepancies. For problem number 2, we have two circuits, circuit A and circuit B, and we're gonna carry out the same nodal analysis for each one. So, well, first of all, we have this circuit in a circle, and here's my rearranged circuit. We have the parallel resistances, the B battery, which is the node after the positive terminal of the battery, the resistances, and then we had three nodes, which are B2, B3, and B4. And then we carry out the nodal equations. Then we get our rearranged equations, and to finally write them in the matrix form. Here we have the MATLAB code, which give us these voltages, and the circuit lab circuit gives us the same voltages, but with minor discrepancies also from the roundings of each program. And then we have also the electric current for each resistance, and then we also have them here. For circuit B, here we also have the well, my rearranged circuit. For me to understand it better, I draw the ground node here. Then we have the B battery here, and we have three nodes, VA, VB, and VC. Then we have to carry out the nodal equations, the rearranged equations, the voltage drop, and its electric current, well, also the matrix. And with the MATLAB code, we could get the almost same voltages as in the circuit lab circuit, and also the electric currents were the same. For problem 3, it involves an electron moving in a uniform electric field generated between two plates. In part A, we calculated the acceleration using Newton's second law, and well, we clear for A using also this other formula, and then that's the answer that we get. It's such a huge acceleration, but it is because electrons are pretty tiny. This means that electrons are accelerating downward because of the negative sign. Then we have the final speed and kinetic energy with units part, which using kinematics, the motion equation, we determine the final velocity, which is this one. It's such a high speed. Then we have the kinetic energy that we get by replacing the velocity that we just did, and it's such a small amount of energy, but big enough for a particle. And then finally we have the time with units. And the time it took the electron to reach the bottom plate was calculated as approximately 3.37 nanoseconds. It is pretty small, but for a particle is good enough. So now for problem 4, problem 4 examines the forces exerted by 4 charges located at the corners of a square. And well, each corner of a square hosts a charge which are 2 positive and 2 negative. Square side is A and the center is 0, 0. We first calculate the distance from each corner to the center using Pythagoras theorem, and we get that r is equal to a over the square root of 2. Then we use the Coulomb's law, and we can substitute the r in our equation. Now we have the coordinates for each charge, and using the Cartesian plane we located, and we give each coordinate a sign. Then we have the first vectors, which we get by using the direction and each coordinate. We have to get clear that similar signs repels and different signs attracts. And then we have here a small diagram of each quadrant. C1, corner 1, corner 2, corner 3, and corner 4. Then we have the unit vectors for each corner. And now using the formula, we get the x and y components. We sum each corner, and we have that in the x component we have a result of 0 as it has asymmetry. Now for the y component we sum them up or everything, and it gave us a downward component that is negative, and all of them go to the same direction, so they summed up. Now for the practical question, we get the previous equation that we got, and we substitute with the information given by the professor, and our final answer is minus 3.26 times 10 to the minus 8 power, which is almost the same as in the MATLAB code, which is here, and with just minor discrepancies because of the decimals. Problem number 5. First of all, we have to calculate the area needed to achieve this capacitance using the given formula. We clear for A, and we get an area of 112.99 meters squared. Now for the charging process, I had these two reasonings. The first one is that we need a t in tau seconds to reach 75%, and that's between 1 tau seconds and 2 tau seconds, and we got 1.4 tau seconds. And to get the only the seconds, we are gonna cancel tau by multiplying RC, which is equal to tau. And for the 75%, we have 1.4 times 10 to the minus 4 power. And then the same for the 50%, which is smaller. So we get 0.7 tau. Um, Now we do the same to cancel tau, and we have 7 times 10 to the minus 5 power. And finally, to the 25%, we will also cancel it by multiplying to RC, and we have 3 times 10 to the minus 5 power. For this other reasoning, we're just clearing for t, and we're getting more exact values for the the maximum charge at those percentages. Then for part number 3, we are using this formula, and we are clearing for t, and we have that to decrease to 30% of its initial value, we have 1.20 times 10 to the minus 4 power seconds. Now for the part 4 graphical analysis, here we have our presented plots, the capacitor charge during charging and discharging, the voltage drop across resistor during charging and discharging, and the capacitor voltage during charging and discharging. Finally, for the critical thinking, the time constant helps us understand how fast or slow the capacitor charges or discharges. After about 5 tau, the capacitor is considered almost fully charged, over 99%, or almost fully discharged. In practical terms, a small tau means the circuit charges or discharges very fast, and a large tau means the process happens more slowly. This understanding is crucial when designing circuits where timing matters, such as filters, timers, or memory devices.